All right, in section 10.1, we deal with sequences as functions. This video is going to be a pretty quick introduction. I'm not going to go very deep into these functions, but hopefully this will be a little bit helpful. I'm going to start off by giving an example of a sequence, which is really just a pattern of numbers, and I'm going to ask you if it's arithmetic or if it's geometric or if it's neither, and we'll talk about them as we go. So determine if the sequence is arithmetic, geometric, or neither. So here, number one is an example of a sequence. Let's see. So I'll give you 3, 12, 27, 48, dot, dot, dot. So we've got some sort of pattern. In order for it to be arithmetic, we need to have the same number added or subtracted every time. In geometric, we have to have the same number multiplied over and over again. So as I look at from 3 to 12, it looks like I added 9. To get from 12 to 27, I added 15. Already, those are two different numbers, so I know it's not arithmetic. Geometric, to get from 3 to 12, I have to multiply by 4. Well, if I take 12 times 4, do I get 27? No, I don't. So therefore, it's not geometric either. That one is neither. If I take 2, 8, 32, 128, dot, dot, dot. We look at that one. From 2 to 8, we added 6, and then added 24. Okay, I'm not adding the same thing. It's not arithmetic. From 2 to 8, I multiply by 4, and then I multiply by 4, and then I multiply by 4. I see I'm multiplying by the same number over and over again. That means it's geometric. That number we multiplied by, we sometimes will call that R for ratio. That's the common ratio in that problem. One more. Okay, negative 5, 1, 7, 13, 19. So from negative 5 to 1, I added 6, and then I added 6 to 7, then I add 6 again, add 6 again, so I'm adding the same number. So that makes this one arithmetic. Okay, now I'm going to give a couple of arithmetic sequence, or maybe one, an arithmetic sequence, and I'm going to ask you to find the next few terms and also graph it. So let's say find the next 4 terms. Find the next 4 terms of the arithmetic sequence. Then graph the sequence. So I'm just going to take the one I already used for arithmetic, negative 5, 1, 7, 13, and 19. So let's find the next 4 terms. Looks like the pattern is we're adding 6 over and over again. So if I add 6 to 19, I get 25, and then I would get 31, then I would get 37, and then I get 43. Those are the next 4 terms. To graph, what I'm going to graph is I'm going to graph the actual term on the y-axis. So we go down to negative 5 even. Maybe I'll go by 5s here. 5, 10, 15, 20. Maybe I'll just graph the initial ones because I don't want to make my graph huge. What I'll put on the so that's the term. I'm going to call that a sub n. And I'm going to call n which term it is in the sequence. Like it's the first term, it's the second term, it's the third term. Those are going to be things we want to get familiar, some notation we want to get familiar with throughout this section. So we could say that negative 5, that's our first term. That's a sub 1. So it is the first term. The n value is 1. So I'm going to go 1 and then negative 5. That was our first point. So I should label this 1, 2. I'm just going by 1s on the bottom. So 2, a sub 2, our second term was 1. So 2, 1 is the order pair that I'm going to graph. So it's going to be about there. The third term was 7, so 3, 7. Be about there. The fourth term was 13, so 4, 13. The fifth term was 19. And what I want you to see here in this graph is, oh, that looks like it's linear. Arithmetic equations are always going to be linear. So when they say sequences as functions, that's kind of the connection we're making. Arithmetic equals linear. So when we write equations later, like in the next section, that will kind of come to life. Let's look at a geometric one. So they get bigger faster, so we're just going to find the next 3 terms. So find the next 3 terms, then graph it. I'm going to go with 1/4, 1/2, 1, 2, 4, dot, dot, dot. So there's the sequence. So the next 3 terms, looks like I'm doubling every time. So we get 8, and then I get 16, and then I get 32. Those will be the next 3 terms. Maybe I'll go by 5s again, and maybe we'll get all the way to 32. 5, 10, 15, 20, 25, 30. My spacing is not perfect, but hopefully it'll be good enough. So at 1, I'm really low, down here at 1/4. Then I'm at 1/2. Then I get up to 2. Oh, sorry, now I'm at 1 right there. Then I get up to 2. Then I get up to 4. Then by the 6th one, I'm up to 8. Then up to 16. Then I get up to 32. So we see that if I connected those, you can't see it, I'm sorry. All my graphs anymore, you couldn't even see. So there's my graph. I apologize for that. So you can see it grows not very fast at first, and then eventually it kind of explodes, and it's going to continue to do that. So that's exponential. So the connection I want you to make in this section is that geometric is equal to exponential. When we go to write the equations for those in a couple of sections, that's good to know. Arithmetic equals linear. Geometric equals exponential. All right, the assignment for this section, what I want you to do, it begins, let's see, on page 663. I want you to do numbers 23 through 27, 34 through 36, 41 through 43, and 46 through 50.